Hey, Algebra 2, let's see. So this is kind of like a couple days, 2 days in one, because we had that snow day. So anyway, this is kind of our third day, even though it's like a third and a fourth day. I'm looking at it as our third actual like lesson working on stuff. And this was about completing the square. So remember, we got a notes packet and a homework packet to go along with this. And so yeah, a perfect square is one where like both side lengths are the same. And so this visual of x plus 4 times an x plus 4 gives us, when we multiply that out, an x times an x makes an x squared, and a 4 times a 4 makes a 16. We get two perfect squared parts. We get that x squared, we get that 16. Great. When we look at that, those are two perfect squares, x squared and 16. But what happens with the other parts? Well, we're going to have a 4 times an x, but then we're going to have an x times a 4. We're going to get two identical parts, and those get doubled. So we actually multiply x and 4, the x and the 4 together to get a 4x, but we have twice them. We have two of them, and that's what we see here. We get 8x altogether. So we saw in class that when we had something squared, we square the first term, we square the second term, and then we multiply them together, you know, a times b, and then we double it. We have two sets of them. Here's what it looks like when it's kind of like foiled out and stuff like that, you know, seeing that we'd have a b times an a and an a times a b. Anyway, if there was a minus sign here, it would just mean that we'd have a negative twice a times b. We'd have two sets of them, but they're negative. Okay, so here's what it looks like in numbers. You could look at these two examples. How would we get this? We'd do 3x times 3x to get 9x, 4 times 4 to get 16. Then we'd multiply 3 times 4 to get 12x, and another 12x to give us 24x, and that's our middle term. If there was a minus sign in between, we would just multiply them again, but now we'd get a negative 6 and a negative 6. That doubles to make a negative 12. And again, we square the first one to get this, and we square the negative 3 to get a positive 9. Okay, this is handy as a pattern because it helps us to find these perfect square problems. So skipping ahead, I'm just going to do all the notes, and then we'll jump in and look at the homework. So I think I'm going to do is two separate videos. This is the homework, the notes video. We saw some problems where we said, hey, you know, here, what if we wanted to complete the square here? What number would we put here that would allow it to be a perfect square? Well, we see it's got to be a 49. Why? We didn't know that. We see that if this is squared and this is our middle term, that middle term would be the combination of two equal parts. A negative 7 and a negative 7 makes a negative 14. So how did we get that? Well, we multiply this times this to get that negative 7. So this has got to be a negative 7. Well, how do we get the last part? Well, it's going to be negative 7 squared, which is positive 49. Here, we have the end parts, these two squared terms, but we don't have the middle part. So how do we get that middle part? Well, we say, well, what squared would make x squared? 9 times 9 would make 81. And if we did x times 9, we get 9x, but we'd get two of them, so we'd get 18x altogether. Okay, so then we saw what that looks like when we're completing the square. We see that we've got something squared and the 10x, and it's equal to 2. Well, that's not a perfect square. So we pretend and we say, hey, they're telling us to complete the square. So put the 2 off to the side, okay? The x squared, the 10x go here, and we put a blank here, and we say, well, what's going to go in that blank? Well, by analyzing this 10 and splitting that into a 5 and a 5, those equal parts, we see that we would have to have an x plus a 5 that would multiply x times 5 to make 5x. Okay, so 5 times 5, that squared would give us this number. We need this number to be a 25, but that wasn't in the original equation. Since we're adding a 25 onto this side of the equation, we also have to add 25 on the other side of the equation. We are now allowed to invent and add numbers if we want to both sides of the equation. It keeps it balanced because now we can take this and we can rewrite it as x plus 5 squared equal to 27. And what do we do to solve this? Well, since it's something squared, we took the root of it plus or minus 27. And then we subtract the 5 from that plus or minus square root of 27, and we get this answer. If this is an acceptable answer, or you can split it up, find the square root of 27, which is 5.196, or negative 5.196, and take away 5 from each of those to get these values. Now, what the heck did we just find? We found x is equal to that. So this is like we're finding the zeros of the equation. We're finding the x-intercepts of the equation. Holy moly. All right. This one, very similar. You can pause the screen and look at the notes for this one. We had to, you know, this 25, we moved to the other side so it wasn't in the way. And then when we do that minus 25, we then put a blank here and complete the square using this information, taking the 10 and the x, putting it here. 10 times 10 would make 100, so we need this to be 100. So we add another 100 to both sides, making this 125, and that 100 allows us to factor this, and we get two sets of answers. Okay. Today in class, we then used that property of completing the square to turn things into vertex form. Okay, so we know that standard form helps us find the end behavior of the parabola and the y-intercept, but that's about all it gives us. The factored form tells us where the x-intercepts are. That's about it. You know, it doesn't give us the end behavior necessarily. You've got to do some more work with it. And vertex gives us one more bit of information. It gives us where the vertex of the equation is, that at 1 and negative 16 would be where our vertex is, the maximum or minimum of the equation. So here's the thing. If we have something in all three of these forms, we actually can now take all three of those forms and we could make a little sketch of the graph, you know. So first, the vertex is at 1, all right, 1 unit and down 5, 10, 15, negative 16 would be right about here. So 1 and 16 would be there. That's our vertex. The factored form tells me that I have an intercept at 1, 2, 3, negative 3, and an intercept at positive 5. 1, 2, 3, 4, 5. Okay, so we got that at 3, negative 3, and 5. This end behavior, by the way, all three of these are the same equation, just turned into each of the different forms. That's why I'm combining the information from them all. The y-intercept is at negative 15, so this right here is where it goes through the y-intercept. And the end behavior here is that it's positive and even, so it's going to be upwards. So this helps us give a better sketch of this parabola. There we go. All three of these give us a complete amount of information. It tells us everything. The zeros, the y-intercept, the minimum point, and the end behavior. We have everything to graph it if we had all three forms. Now, typically, we're using these forms strategically, like we're using the vertex form to find a maximum or a minimum height of something, or we're finding the zeros, the x-intercepts, to say, well, when does something get launched and when does it hit the ground? Or is using the y-intercept to say, well, you know, maybe how far up the y-axis is something being launched? Is this somebody like holding a basketball 6 feet above the ground and then taking the shot? And that, you know, so all right, let's see. What else did we do in class? So then, again, mini lesson. Then we had this problem here, which was basically like, if this is in vertex form, which it is, it fits that vertex form, what are the h and the k values? So we want the opposite of this value. That's what this like negative h here means that we can do. We want the opposite of this negative 1. So the h value is a positive 1. The k value is the same value that you would, that positive 3 is what we use. So what does this mean? At 1, 3 is where our vertex is for this graph. So that's where the minimum value is for it. And then, oh boy, then we saw equations like this. And we used a little trick to complete the squares. All right, so we completed the squares, we turned it into this like, this vertex form. We found the coordinates of the vertex, we graphed it. There's a lot here. If you missed class these past couple of days, you really did miss a lot. So I'm gonna do a second video now going over the homework where you'll see me go over a couple problems like this in detail. So that's why I'm not gonna go over these in detail.